Introduction to Electrostatics, a beginner's guide. Electrostatics is the study of electric charges that are not moving. We encounter electrostatic effects all the time, like when we rub a balloon on our hair and it sticks to a wall, or when we get a small shock after walking across a carpet. This happens because electric charges can build up in certain situations and create forces that affect other charges. At the heart of electrostatics are electric charges. These charges come in two types, positive and negative. Positive charges are carried by protons, particles in the center of atoms, and negative charges are carried by electrons, smaller particles that move around the protons. In nature, like charges repel each other, positive pushes positive, negative pushes negative, while opposite charges attract each other, positive attracts negative. One of the most important laws in electrostatics is Coulomb's law, which tells us how charges interact with each other. According to this law, the force between two charges depends on how big the charges are and how far apart they are. The bigger the charges, the stronger the force. Also, the closer the charges are to each other, the stronger the force becomes. Next, we have the concept of the electric field. This is a way of describing how a charge affects the space around it. Imagine you place a positive charge somewhere. The electric field would be the invisible force field that other charges would feel if they entered that space. For a positive charge, the electric field points outward, away from the charge. For a negative charge, the field points inward, toward the charge. The electric field tells us the strength and direction of the force that another charge would feel if it was placed at a particular location. Electricity also involves the idea of electric potential and voltage. You can think of electric potential as the stored energy that a charge has at a specific point. Voltage, on the other hand, is the difference in electric potential between 2 points. This difference in potential is what causes charges to move, which is how we get electricity flowing in circuits. In materials, we encounter conductors, insulators, and dielectrics. Conductors, like metals, allow charges to flow easily through them. That's why we use copper wires to carry electricity in circuits. Insulators, like rubber or plastic, prevent charges from moving, which is why we cover wires with insulation. Dielectrics are materials that don't conduct electricity but can still be affected by electric fields, which is important in devices like capacitors that store electrical energy. Another important idea is Gauss's law, which helps us understand how to calculate electric fields in situations where charges have special shapes, like spheres or long straight lines. This law tells us that the total electric field coming from a charge can be calculated based on how much charge is present inside a certain area. So, we introduced the concept of the electric field, which represents the influence that a charge exerts on the space around it. Now, we need to explore the electric field in more detail, as it plays a key role in understanding how charges interact. The electric field at any point in space is a vector quantity. This means it has both magnitude, how strong the field is, and direction, which way the field points. For a positive charge, the electric field points away from the charge, whereas for a negative charge, the field points towards the charge. This is an essential concept in understanding how forces act on other charges placed in that field. The strength of the electric field also depends on the distance from the charge. The further you move away from a charge, the weaker the electric field becomes. For example, if you double the distance from the charge, the electric field strength will decrease by a factor of 4. The electric potential at a point is closely related to the electric field but has a different interpretation. While the electric field represents the force per unit charge, the electric potential represents the potential energy per unit charge. When a charge moves within an electric field, it gains or loses potential energy depending on whether it moves toward a positive or negative charge. This concept is useful in determining the work done by electric fields when charges move within them. Voltage, or potential difference, is simply the difference in electric potential between 2 points. It provides the driving force that causes charges to move, which is essential for the flow of current in electrical circuits. Higher voltage means a greater potential energy difference, which typically leads to a stronger electric current if the circuit allows it. One of the most important tools in electrostatics is Gauss's law, which relates the electric flux through a closed surface to the charge enclosed within that surface. This law is especially useful for calculating electric fields in systems with high symmetry, such as spheres, cylinders, and planes of charge. The electric flux through a surface is the measure of how much electric field is passing through that surface. Gauss's law tells us that this flux is directly proportional to the charge enclosed by the surface. Gauss's law can be applied to a variety of charge distributions. For example, for a spherical charge distribution, the electric field at any point outside the sphere is the same as if all the charge were concentrated at the center. This allows us to calculate the electric field around spherical objects without needing to consider the complicated distribution of charge in detail. This principle is also used in calculating the field from long, straight wires or infinite planes of charge, where symmetry makes the application of Gauss's law particularly powerful. Capacitance is a key concept in electrostatics, particularly in the context of capacitors, which are devices used to store electrical energy. A capacitor consists of two conductive plates separated by an insulating material, called a dielectric. When a voltage is applied across the plates, electric charges accumulate on the surfaces, creating an electric field between the plates. This field stores energy, which can later be released when needed. The ability of a capacitor to store charge depends on several factors. The surface area of the plates: larger plates can store more charge. The distance between the plates: the closer the plates are, the stronger the electric field, which increases the capacitance. The dielectric material between the plates: dielectrics increase capacitance by reducing the electric field's strength, allowing the plates to hold more charge at a given voltage. Capacitance is measured in farads, F, and for a simple parallel plate capacitor, the capacitance depends on the area of the plates, the distance between them, and the dielectric constant of the material between the plates. Capacitors are important in circuits because they can store and release electrical energy, which is used in filtering, timing circuits, and many other applications. In the presence of an electric field, the behavior of materials can be understood in terms of conductors and insulators. A conductor is a material that allows charges, usually electrons, to move freely. Metals like copper and aluminum are excellent conductors, which is why they are commonly used in electrical wiring. In a conductor, charges move in response to an external electric field, and they distribute themselves in such a way as to cancel any internal electric field. This is known as electrostatic shielding. The electric field inside a conductor in electrostatic equilibrium is zero, which means that no force acts on charges within the conductor, and all the charges reside on the surface. On the other hand, insulators are materials that resist the movement of charge. Rubber, glass, and wood are common examples of insulators. In insulators, charges are bound tightly to their atoms or molecules and cannot move freely. The electric field inside an insulator can exist, but the material itself does not conduct electricity. A dielectric is an insulating material that becomes polarized in the presence of an electric field. While dielectrics don't allow current to flow, they can store electrical energy. This property is crucial for capacitors, where the dielectric material increases the capacitor's ability to store energy by reducing the strength of the electric field. In electrical engineering, electrostatics plays a crucial role in understanding and designing circuits, particularly when dealing with capacitors, electric fields, and insulating materials. For instance, the design of capacitors for energy storage, understanding the behavior of electric fields around conductors and insulators, and applying Gauss's law for calculating fields in symmetrical systems are all key aspects of electrostatics.